let's say at the start of this test, of this experiment, we have two deers at a park. We have two deers, and they make up the initial population. The initial population is 2. And let's say 1 year passed. 1 year passed, and each of these deer have a baby. This deer has one baby. Let me represent that with another orange dot. This deer has another baby. So overall, how many deers do we have? Well, we have 1, 2, 3, 4. Now we have 4 deer. And let's say another year passed, and each of these deer has another baby. So we are going to have 4 more babies. 1, 2, 3, 4. Now how many deer do we have? We have 8 deer. We have 4 and we have another 4. Let's say another year passed, and each of these 8 deer have one baby each. Let's say deer grew up really fast, become an adult, and I know this isn't really realistic, but for the sake of this, let's assume they do. And each of these deer after 1 year has one baby each. So now we're going to have 8 more babies, 8 more deer babies. 1, 2, 3, 4, 5, 6, 7, 8. So how many deer do we have by the end of third year? Well, we had 8 and we have another 8, so we have 16 deer. So now what I want to do is plot this. Try to graph this on the coordinate plane. And let's say this is the year. Let's represent that with time in years. And let's put population. Let's make it p-axis. That's the number of deers. Number of deer. And at the time 0, we have 2 deers. We have 2 deer. We have 2 deer at the beginning. At time 1, now we have 4. At t equals to 1, we have 4 deer. 3, 4. That's where we are. Let me move this dot. Let me move this away. Let's move 1 to further right so it's easier to see how the graph is going. At time equals to 1, we have 4 deers. What happens when t is 2? When t is 2, we have 8 deers. Let me move this up. Let me extend this. Let's go up. We have 8 deers. 4, 5, 6, 7, 8. At t equals to 2, we have 8 deers. What happens when t is 3? What happens when t is 3? We have 16 deer. 8, 9, 10, 11, 12, 13, 14, 15, 16. At t equals to 3, we have 16 deers. And now let me try to graph this. If we try to graph this, it's going to look something like that. It's going to look something like that. And you can see it's not a line. It's not a line, which means the rate of change is not constant. Its rate of change is actually increasing in this case. And what's the name for this graph? Well, we call this exponential growth. Exponential growth. And in the previous video, we saw that exponential growth can be represented by differential equation y prime is equal to ky. The rate of change of y with respect to time is some constant times y. But here's my question to you. As time passes and passes, is it possible for each of these deer to have another deer each and the population to keep on growing exponentially? Or it's going to hit some boundary and start decreasing? The rate of change of population starts to decrease until it reaches some limit to the population, which the population cannot grow above 2, or it's going to decrease on. Let me explain what I mean. Let's say time goes on and let's say we have 120 deer at some point. Well, if we have too many deer at a certain point, the lack of space, lack of food, disease, predators, those kind of limiting factors can come into effect, and they can lessen the growth of population. Let me graph this suburb thing down below. At first, the population seems to be growing exponentially, but at some point, as more and more population come into play, there are going to be limiting factors are going to come into more and more effect, and it's going to start to die down. The rate of change of population is going to start to decrease until it hits some asymptote. This makes sense. If your population is keep on growing and growing, you're not going to have enough space, you're not going to have enough food, and some of the population are going to die down, and you are not going to have this one deer per one child thing. As the time goes by, some deers might die because of lack of food, some deer might get bitten by some kind of predator, and it's going to die down into a line, and we call this line L, we call this asymptote, we call this carrying capacity. Carrying capacity, the maximum amount of population and environment can support for indefinite amount of time. And we represent this with capital L. And here's my question to you. We know if we want to represent exponential growth, we can use the exponential differential equation y prime is equal to ky. How can we represent this kind of motion? How can we represent this graph where it's which is kind of exponential at first, but it dies down into kind of exponential decay until it hits some asymptote? How can we represent this with a differential equation? Well, let's think about this. We want to represent this graph in terms of the rate of change of y with respect to time. Well, if we really think about it, when the population is very close to zero, or population is far away from the carrying capacity from L, the graph almost looks exponential. At first, the graph looks very exponential, which means it's going to somewhat related to dy dt is equal to ky. But as the population grows and gets closer and closer to L, the rate of change, the slope of tangent line becomes more and more horizontal, which means as y approaches L, the rate of change of y with respect to time is approaching zero. It's becoming more and more horizontal, and you're not going to have more deer. The rate of deer population is going to grow at a slower and slower rate until it becomes almost very close to zero. Until it becomes very close to zero. So how can we represent that using differential equation? Well, here's the thing. We want to multiply this by some kind of expression, and here's what we want this expression to do. For this expression, when y is very close to, when y is far away from L, when y is close to 0, or when y is far away from L, or far less than L, from L, we want this expression to be close to 1. Close to 1. Why do we want it to be close to 1? Because if y is far away from L, the growth is going to be almost exponential, which means we want this to be ky. We want this to be ky times something very close to 1, because ky represents exponential growth. But if y is very close to L, we want this expression to be close to 0. Which is going to signify the rate of change is becoming more and more closer to 0, and the population isn't growing as fast enough. So how can we represent that? And one way the environmentalists and mathematicians thought about it is by multiplying 1 minus y over L. And let's see how this accomplishes our goal. When y is far away from L, let's say y is 0.001, well, 0.001 over L is going to be something very close to 0. So 1 minus something very close to 0 is going to give you 1, about 1, which is going to let this become ky, which is exponential growth. On the other hand, if y is very close to L, we're going to have 1 minus something like y over L, which means it's going to be something like 1 minus 1, or dy dt equals to ky times something close to 0, or the entire thing becoming close to 0. So this dy dt is equal to ky times 1 minus y over L. This differential equation can be a better method of representing the growth of population as the time goes by, because it's not always going to grow at exponential rate. Environment and limiting factors are going to come into effect. And is there a special name for this? There is, and we call this logistic differential equation. Logistic differential equation. And on the next video, we're going to attempt to solve this. We're going to attempt to solve this for y.